All right. In our first example, we're going to verify the Cauchy-Riemann equations. So let's look at this polynomial. F of z is z squared plus z. First of all, it's a polynomial. So this is analytic everywhere. Analytic means, in this case, it means being analytic everywhere is, in this case, equivalent to being differentiable everywhere. And we say this is an entire function, just to remind you of the terminology. All right. So all we're going to do is verify the Cauchy-Riemann equations. According to the theorem we just proved, they should hold everywhere. There should never be a point where they fail to hold. So let's do that. So we have to first work out the real and imaginary parts of f. So oops. So what are u and v in this case? So we're going to replace our z with x plus iy and then see what they are. So we've actually already done z squared. Z squared we can rewrite as x squared minus y squared plus 2xyi. But then we're adding z to it. So let's move that let's move that x squared over. And then we'll factor out I from what's left. Great. So this is our u here, and this is our v. Okay, so now let's work out the first order partials of u and v. Notice that these functions u and v are again polynomials, and the partial derivatives exist everywhere, as the theorem told us it would. So I'm going to introduce some notation here. Writing partial u, partial x, and so on is usually tiresome. So we write u sub x to mean partial u, partial x. And so we differentiate with respect to an x. We have 2x. From that, the y squared goes away, and then x will give us a 1. And then again, u sub y is going to mean partial u, partial y. And so that's, let's see, the x terms don't matter, and then we have negative 2y from the y. And then vx looks like it's going to be 2y, right? Because the x goes away. And then vy looks like it's going to be 2x plus 1. All right, so those are our first order partial derivatives. In the Cauchy-Riemann equations, that I'm going to abbreviate as CR, tell us that ux should be vy. Is that true? I think so, right? They're the same. Great. And it tells us that uy should be negative vx. So here's uy. Is that negative vx? Yeah, it is. Cool. All right. So this is an example just to verify that the Cauchy-Riemann equations indeed hold when our function is analytic. Let me also point out that there's a converse to the Cauchy-Riemann equations that we're going to investigate next. Namely, if we found that this wasn't true somewhere, then we could deduce, for example, that our function was not differentiable there. Because if it was differentiable there, then they'd have to agree everywhere. So the next example is going to delve into that a little bit to actually apply the Cauchy-Riemann equations to prove something is not analytic. Now I'll also mention that in a minute we'll show that actually the theorem is an if and only if. So with appropriate conditions, to check if you're analytic, all you have to do is you have to compute these partial derivatives and then check the Cauchy-Riemann equations with them, which is incredibly powerful. So what I'm trying to get here is this example might seem a little silly. It's like, oh yeah, it works, but actually these equations are incredibly important, and they'll help us develop a criterion for differentiability so that we don't have to do any of these complicated complex limits.